Welcome back, everybody. It's time to start next lecture. Today we are going to discuss on data association. But before, let's do a brief summary of what we did on Tuesday. Right, so if you remember, we talked about EKF SLAM. So we have discussed like several uses of EKF so far, right, for localization, now for SLAM as well. In this case, there were like some particularities that we needed in order to use EKF, right? And it was the following. So we also discussed like what's the difference between online or full SLAM, right? Basically, we are just interested in last pose, while full SLAM approach would be calculating the full trajectory, right? So we'll talk about it in next lecture. Okay, so what we had in this lecture was this. So we want to estimate this belief, right, given like some observations, some actions, and then we were also introducing these correspondences, right? So the solution that we discussed, it was very easy. We defined an augmented vector, right? We were just including here state of our dynamic system and then other variables that we wanted to estimate, which in this case they were not dynamic, right? Landmarks are just, well, for now, you can define them as static positions in our map, right? So we created an augmented vector, and with this we redefined the transition function now, like this. So we are propagating the full state. The discussion was, sure, so if landmarks are static, then we need just to reformulate things, and if you remember, they were not moving. That means that the Jacobian was 0, obviously because there's no perturbation here and other little things. But at the end, as a result, what we got is the right equations to be applied in the EKF, right? So in this case, this function was this. Okay, and then the same happened for the observation function. So we had an observation function, and in this case, we need to relate this to the augmented vector. And if you remember here, as a result, well, because this Jacobian, not all terms were 0, it was not as easy as just consider all dependencies with respect to landmark 0. There's actually one landmark that matters, and it's the one that is describing our observation, right? So at the end, the Jacobian looked like this. We have our Jacobian that we have described previously with respect to the state or pose. And then a lot of zeros except for the landmark that we are observing, right? Okay. So I think, oh yes, and then we also describe what to do when we have new landmarks, because the whole point of this is not really augment the state and then just keep doing mapping. The point is that when we are certain that there's new observations, new landmarks that we should be including in our map, because we move away from the current scene or we haven't observed that landmark for whatever reason, but we need to consider new landmarks. Well, this is what we were doing. So the mean of the new landmark, we describe this inverse function, which is for now the best we can do. So we don't know this location, but we can invert this observation function. Remember, the observation function, if we have here a landmark, and we see like this observation, right? So with this, we can also create an inverse, right? So it's not just from this state, oops, this state and this landmark that we can, I mean, this is what the H function will give us, right? With respect to state and landmark, we'll give the observation, but we can have the inverse, right? Just with this observation and the state, we can actually give the position of this landmark. Right, and then what we do, we evaluate this at the mean, because this is our best approximation so far. So then, what else we were doing? Our new mean, it's just going to be this augmentation again. So this is what we had before, and this is new mu. And then if you remember, the covariance has to be updated, right? And it looks like this. So we are not, I mean, these subblocks shouldn't be changing because we are just adding a new observation. This was our previous propagation with whatever number of landmarks. Now we have an extra landmark that we are adding into our augmented state, and basically all this part in the covariance should be updated. Not just this block, right, which will be representing the yes, we have a new landmark, but also these cross terms that are relating this landmark with respect to previous things, right? Okay, so that was last lecture, right? Before moving on, I have one comment. So, okay. Well, maybe I have more than one comment. So the first one is, this Friday, you should be submitting groups, right? So yeah, we have in our group 3 people or 4 people, or we have 2 or 1 or whatever. You should be submitting this, and then by next week, we should have like groups established. Also, so groups, send list. Right, you send list over Telegram, on email, or in Canvas. Yeah. Okay, the second thing is next week, once you submit these groups and we give like a final, we are going to be doing like short interviews in case that you want, right? So we'll go there with all your group, and then we are going to be discussing, oh, okay, so which topics do you have? Just first thing comes to your mind. We have discussed some things, not all the content of the class. Actually, the most interesting part will come in next lectures. There's lectures from, I mean, there's papers related to these future lectures that are already in Canvas, in case that you want to take a look. I think some of you have already discussed, like, look, I'm working on this problem. Is this a good project? So in general, yes, we are open to many kind of projects. But with this meeting, I think we will have a better idea of exactly what the project is going to be about. And then later, we are going to do a proposal, probably not next week, but in 2 weeks. Okay. No, this will be in office hours. But if you remember, we have after each class, like 1 hour for office hours that we stay here, and then we also have office hours on Friday. So you will say, look, our group can meet, I don't know, Tuesday, Thursday, right? And then we will arrange, we will confirm that the schedule is right, because I mean, all of you cannot come at the same time. That will be not very optimal. So we will try to arrange things. But I think the first step is this, right? So we will arrange all groups in case that groups are not final. We will mix, merge groups or whatever it's required, right? But everyone should be like on a group of ideally 4 people. And yeah, I think yeah, that's the first step. Okay. So any question on this? I think, yes, we have the Telegram chat for these particular questions, but who has already started talking with colleagues next to you, other people about groups? Okay, so yeah, if done, maybe during this break, you keep talking. Okay, so now let's talk about data association. Right, data association, what is this? If we were saying that this was given last time, and remember that this is the correspondence of each observation matching the J landmark, right? So in general, this equals J. It's just an index of whatever landmark we have. Oops. Right, so we have this set of data associations. Now the problem is going to be, okay, so how can we estimate these associations, right? And basically the outline of today's class is we are going to start with simple examples, right? Doing like strong assumptions, but that result in easier algorithms, and then we are going to move on into more involved approaches, right? So at the end, you will see that we can provide like a complete algorithm for solving this data association. Still, this is a very vast topic, right? So here, I'm just going to describe what is the problem in general, what is the general approach, right? So we are always talking about probabilistic way of solving things. The same happens for data association. And well, at the end, this is the only important message of today. We want to estimate this vector of correspondences. Okay, so if that is clear, then let's talk about the first approach that you can use, which is, we'll see that it's not the best one. It's not actually good, but the Euclidean nearest neighbor. Right, and I think this is the most intuitive. So how can you associate landmarks? Just take the closest one, and that's it. So let's see what happens with this approach. Okay, so the problem is as follows. We always have like our state to be a two-dimensional pose, or this could be whatever. But well, yeah, most of the time it's going to be a two-dimensional pose. Now, what we have is, for example, a couple of landmarks, right? This is going to be landmark number 1, and this is going to be landmark number 2. Okay, and then we have some observations, right? And remember that these observations are whatever the sensor is giving us. So in this case, this is going to be Z1. And this is Z2, right? Indices matches, but remember that it's not always the same, right? So here, in general, we use subindexes for landmarks J, and then for observations I, right? This way. So it's just a coincidence, but you can think about it as, yes, subindexes here matter. Okay, so then what is this nearest neighbor approach, what it's doing? So just intuitively, what it's doing is it's looking for nearest neighbor using Euclidean distance. So in this example, it's almost trivial, right? What is the distance with respect to Z1 to landmark 1? It's, well, this, whatever it is, and to landmark 2 is this, right? So this will be closer, and the same happens for number 2, right? So second observation, this is the distance to this landmark, while the distance to the first landmark is much bigger, right? So again, this is the first approach. We always start with the intuition, easy algorithm, and then we'll see how things will evolve, but let's try it this way, right? So for each observation, for each observation, what we are going to be calculating, as I said, is the minimum distance, right? So that landmark that is on the minimum distance, that's going to be our nearest neighbor. Okay? So nothing complicated here, and this is important, so we are using just Euclidean distance. Okay, so the algorithm is as follows. We need to do like exhaustive search. So basically for each of these observations, right, that goes from 1 to, in this case I was using K, right? And then for each of these observations, we are gonna match we are gonna calculate the distance. So that means that for each of these observations, we need to also loop for each of the landmarks, right? And here I'm using N. Okay, so we have these two force inside, and then basically it's just going to be this, right? So, well, CFT of I equals mean okay, so this is what I explained before. We just go to all these pairs, observations, landmarks, and then we just rank them in, right? This is the most straightforward thing. But let's see a little problem on this approach, right? So here we have these two force. Well, basically the complexity depends on the number of landmarks and, well, the number of observations and the number of landmarks. So it's hard to do better than this, but we'll see that if we take like other considerations, it's going to be much harder. This complexity can be like pretty worse than this. So basically what we do is we match each observation to the closest landmark. Right? It's relatively fast because we are just calculating a bunch of distances. So this is a good thing, but the problem is that this is a greedy optimization algorithm, right? We don't care about the context. We are just looking at whatever is best solution individually, right? And this can create some problems. So imagine we have a third observation here. What is our algorithm going to say? That we're observing the same thing, right? There's no other landmark, so just based on this, you calculate distances with respect to landmark 2, and that's it, right? We are just going to be like sometimes doing like things that might not be logical. Okay, so greedy data association. Right, so this is not a very desirable thing. Actually, could be bad, depending on the context, because there's usually a lot of information, but it's fast, and this is a good property. And then we are basically matching like things on an okay way. Okay, so this is the first thing that anyone would try, right? You just look whatever is closer. Now, we have always argued during last lecture so that we don't have like, we always have this measure of, we want to have like a measure of the uncertainty on each of the variables that we have. So that means that there's going to be distributions for almost everything, including landmarks, right? So after EKF SLAM, we also have like the covariances for each of these landmarks. So the next step would be, okay, instead of just doing this Euclidean distance, which might not be always the right decision, let's use another distance, which is the Mahalanobis distance. Right? This was defined in lecture 2 or 3. Yeah, but now we'll see an application of this. Another one. Yes. Yes, greedy data association. What I mean by greedy is this example that I gave. Greedy doesn't think, I mean, the algorithm is not taking the global context. So you can have these kind of situations for greedy algorithms. You see two observations. Clearly, you know that they are two different landmarks for whatever reason. But this algorithm, by design, is going to assign the two observations to the same landmark, because there's no way to have like global consistency on this greedy approach. So that's what greedy means. It's fast, but it's not calculating context for other solutions. So in this case, whatever solution is for number 2 will not change the minimum to the observation number 3. Okay. We will define like a better way of handling things like in a context later. But for now, well, we started with this just distance, Euclidean distance, and now I'm going to change slightly the history here. So we have a, oops. Oh. We have a landmark. As I said, we have access to the covariances, right? Because our augmented state is giving augmented covariances, and the covariance of each landmark, we know where we are, right? So you can basically marginalize all other variables and get your covariance, right? So here again, we have landmark 1, and then we have landmark 2. Right? For whatever reason, landmark 2 is much more certain. We have observed this many times, or maybe we had a prior observation or a prior belief, someone giving us information about this, but the fact is that landmark number 1 is very uncertain, right? So we have this, remember, this is the two-dimensional ellipsoid of 1 sigma, for instance, right? So here, then, observations are going to be affected also by this, right? So in this case, we might have this observation, right, set 1, and then we might have this other observation, right, set 2. So in terms of the uncertainty, what we can say for sure is that since this covariance is large enough, right, this observation and this landmark are not that far away, right? So you can say that they are close, at least in probabilistic terms. Because the information here that you have is not sufficient to say, no, look, this is another thing. You shouldn't be taking a look at this. While maybe this Euclidean distance is the same, right, between second observation and landmark 2, but probabilistically speaking, and that's why we are using the Mahalanobis distance. Remember, the log of probability of a Gaussian, it's, well, Mahalanobis distance multiplied by 1/2, right? But in these terms, then this observation with respect to this landmark will be far. So it doesn't make sense to match them together. Maybe you have a new landmark, right? Maybe this is some observation that you shouldn't be taking into account. We will discuss later exactly, well, what to do, because this is also like not very principled. It's open to many solutions that we can do, but this notion of distance, I think it's important because this changes the problem. Oh, thank you. Okay, and unless you're going to open it more? No. Thank you, yeah. Okay, so let me write it this way. Now we have distance observation I to landmark J, right? And it's almost the same as before, but remember that the Mahalanobis distance, what it's taking into account is the covariance, right? So in this case, it's the covariance of the observation. Okay, so another way of writing this, if you want like a little more compactly, we have this vector, this difference. And then Mahalanobis, it was just this product of this vector, right? So, okay, so the great thing about this is this Mahalanobis distance is capturing uncertainty, right? This is going to be helpful. Why? Because why do we care in defining covariances in the first place, right? If we are not going to be using it. So but still, if we do the same algorithm, right, which was we just iterate over all observations and then we iterate over all landmarks, and we just find the maximum one, we still have kind of the same problems. So it's going to be as efficient as nearest neighbor's Euclidean distance. So this is good. It's a little more robust to noise. simply let's say that it's more robust, because here we are capturing this idea of uncertainty. If some landmark is not well estimated, so that means that this gives us like this margin of considering, okay, so maybe we were not sure before, but we should be associating, while if you are certain, then it's easy for you to filter growing observations, or maybe decide that there's a new landmark. But still, this is greedy, right? So there's not really, we haven't solved really like all our problems before. We are simply giving like a little more robust distance function. Okay, and then I'm gonna do like, so what would you do if you have like this kind of setting, right? Imagine now this is like mental data association solving for you, right? So what would be your algorithm? You have 2 observations and 2 landmarks, right? No. So okay, not how, which algorithm would you be using? So in this case, how would you be solving the data association, right? So in this case, would you associate observation 1 with landmark 1 and associate observation 2 with landmark 2? So you will doing this observation, this association, 2 and landmark 2 and 1. So who would associate landmark 1 and observation 1? Okay. Yeah, sure, why not? I mean, it makes sense if we're still inside, but who will associate landmark 2 and observation 2? Okay, so that's a bad idea because you have already a very certain estimation. You have a question or you are with group number 2? Okay. Exactly. Yes. Exactly. Well, any kind of distance, but the thing is that the number of distances that you have to calculate is the product of number of observations multiplied by number of landmarks. So if you want, you can do this like in matricial form and then look for max for each row, or you can do 2 fours as we have done. But exactly. Yes, absolutely. Hold on. Yeah, it's a very good question. I'm thinking that maybe we can give. Okay, so your question, if I understood correctly, is you are saying that it's not assumed that it's going to be a fair matching. Not all observations are going to match all landmarks. There's no assumption that you are going to be observing all landmarks. So basically, it's going to be like unfair association. And on the other hand, it's also true that you can observe new landmarks. So that means that this pairing is not assuming that every observation should be associated with a new landmark, because maybe all observations are new landmarks, all of them. Right, so there's not, I mean, this will be an extra constraint that will make the problem easier. If you just go, you find like max on all of them. But here you have also this null hypothesis of, oh, we have a new landmark, right? So this adds like a little more combinations here. Is this answering your question? So I'm just here giving 2 observations in 2 landmarks, but, oops. Right, no problem. But then, so getting back, so this K, usually it's not equal to n, right? But getting back to this second question, right, which was not that clear, are we going to associate second observation with second landmark? You have some people were saying yes, others were not saying anything, which I guess it's no. So who would say that this is a new landmark? We have also people saying that it's a new landmark. And then there's a third option. Who would do nothing? Unless, raise your hand. Yeah. So we have people, yeah. So we have these three options, right? I think all of them are reasonable. There's no clear winner here. Depends a little on the problem, right? Depends on how you want to treat your new landmarks, how you, I don't know, maybe this is a very unlikely event, and of course you should be observing a new landmark. Maybe you have noisy sensor and you need to be aware, so you need persistent observations of new landmarks until you tag them as new landmarks. Or maybe the observation noise is that great that still, in terms of well, no. But still, okay, it could be possible that this corresponds to the second landmark. I'm not talking about, because here we should be calculating the covariance after propagating also like state, observation, and the landmark. But for now, I'm not doing that. I'm just saying, look, just based on the covariance of each of the landmarks, this is far away. So we have these three options. What to do? This is open question. What the probabilistic robotics book says, basically, this is a hard question. This is what it says. You can read a little more about that, because there's a good explanation, but here I'm just going to write like, what can we do? And I think one of your colleagues already talked about this. So if this is the Mahalanobis distance, right? Then maybe if you are here, and this is going to be whatever threshold you decide, maybe 1 sigma, maybe, I don't know, 3.5. This is the hard part, estimate this threshold, right? But let's say that from 0 to this, oh no. And then with this, we associate. If we are really, really far away from anything, then maybe we need to associate a new landmark, right? We need to decide, look, this doesn't correspond to anything. And for this, as I said, you can also observe like persistently. If you see like the same landmark, the same new landmark again, so that means that you should not always initialize the moment that you see something, right? Because there's might be a lot of noise in your sensor. But this is another strategy, right? So you have a second landmark, a second threshold. Okay, and basically there's here a region. Depends on you. It might be 0, right? These two thresholds might be the same depending on what you decide. That basically it's do nothing, right? So this part is not well established, although we have this probabilistic measure of this, let's say, test of landmarks versus observations, right? There's still like a lot of things that are not so clear. We don't have an answer just with these probabilities, with these distributions, because the problem of decision making by itself, it's a little more involved, right? But people, I mean, if you go on the book, there's I think a very good discussion on this, and this can be also part of, I don't know, if you are implementing this, I believe not in problem set 3, but before, basically it was this decision, what to do with these new landmarks, right? So here you have like some hints on what to do. Okay, so let's move on to a little more principal things. We have a question. How can you define a threshold on an heuristic? Usually it's something given. There's not a magic recipe for you. It's usually tuning parameters, taking a look, observing what's happening, right? And then you, but usually this is a hard part, right? So this hyperparameter tuning is the hardest part that no one talks about that in algorithms, right? But it takes a lot of, I mean, actually, it's critical to the algorithm by itself, and it's not clear exactly how to obtain them. Okay, so yeah, in general, stay away from hyperparameters, but sometimes, yeah, that's... Okay, let's talk about another approach, which is the maximum likelihood. I'm going to redefine things. So if these approaches were greedy, we were just ranking all distances and saying, okay, who is closest? You, okay, so this is kind of the greedy approach. With this, let's try another more general approach, and after doing some assumptions, we'll see where we end up. We have a party, right? Okay, well, don't get this turf. Maximum. Are you invited? No one invited me. No? Is this a party for students, or this is a party that it's happening? No one knows? Not for students. Oh. Okay, well, it's very unfortunate then that we are suffering here all these preparations and no one is assisting. Okay, so let's discuss on the maximum likelihood for data association, right? So we know that maybe we can redefine this from the base filter, from that now, so I'm not really going to derive this. I'm just going to put like some equations for you to get the idea of how hard it is, right? But maybe what we want to estimate is our full trajectory. And at the same time, we want to calculate all these correspondences. So remember, they go from 1 to t because observations start at it, at time 1. And then we have some observations, and well, in case of, no, actually no. Okay, well, this is x, but we could be writing here augmented vector, whatever it is. Okay, we have this. So if we applied here the product rule, we might have something like this. And then, yes, we have this. Right, so this is just the product rule. Oh, I think it's not very clear. Okay. So then we know what to do with this. This is our old base filter. From this we can derive our Kalman filter for SLAM, for localization, for whatever. In this case, yes, this is, well, SLAM could be. And then we have this term after doing this factorization that is a little more confusing, right? And basically we need to find a distribution given all our trajectory, all observations and all actions to calculate what is this sequence of correspondences. And here what I'm writing is this. The correspondences from 1 to t is this. Correspondences at time 1 for all observations, correspondences at time 2, and go on until we get here, right? So basically we have a sequence of correspondences that we have to do. Here, we cannot really do the assumption of this is also going to be a Markovian, I mean, the Markovian property is going to hold for this. Why? Because maybe a wrong association can be corrected later, right? So that will depend on the full trajectory. And basically with this, I'm not going to go deep into this derivation. That's not the point. The point is that this distribution is really, really hard to calculate, right? Because every time that you have a new observation, maybe you would need to change the correspondences at past, at past states, right? So that makes that you need to reevaluate things constantly. Basically, this is really hard doing this like exhaustively and correctly. So as always, we are gonna do some assumptions. You have a question? No. Okay. So. Well, let me just write this. So hard to calculate, right? We need some assumptions. And the first one is very reasonable. I would say that the first one it's always taking, and it's going to be this. We take data association incrementally. Right? What does this mean? That once we calculate, well, hold on, solve data association incrementally. Right? So that means that we are not going to get back. We are not going to reevaluate associations. If there's a mistake in the past of the association, that's fine. We just care about, let's say, current time, right? So with whatever observations we have and whatever state estimated we have, we are just going to be calculating what is this probability of correspondences, right? So what is the motivation for this? Actually, this is assumption one. The motivation is maybe you have a filter. You are filtering things online, and you cannot really go back in time, right? Once you have calculated your state variable, you cannot really undo things. I mean, that will be when you calculate full trajectories. So it doesn't really matter what wrong associations you did in the past, right? If your task, actually, if your problem is a filtering problem where you need the latest estimate of your state variables, then it's an okay assumption. You might be introducing noise, but we will just deal with that. Okay, so this written here, history of correspondences. Only depends on the last correspondence. Or it's a last estimate. Okay, and then although we know that that might not be true, what is implicit here is that previous correspondences are correct, right? So we assume them to be correct, although we might have introduced some noise, and then we move on. Okay, so this basically prevents us from reevaluating things constantly, which is a little tedious for all filtering approaches, right? We'll see when we talk about batch optimization that maybe this problem is not that bad, right? We can do evaluation of all correspondences like back in time, and still the penalties for that are not going to be that great. Okay, so previous correspondences were correct. Okay, so this is a reasonable assumption for some of you, maybe. Yes. Yeah. So what I'm using here is the independence, conditional independence assumption. Right? So it doesn't matter if you condition with the previous correspondences that you have. Basically, all it matters is your state and your observations. So in this case, your previous correspondences are in the, there's conditional independence, right, on this estimation. We are going to talk about that now, because for doing this, we are going to basically derive it, doing some manipulations with base, and then you will see that actually this distribution factorizes into something. But this will be in a minute. Yes? Yes, yes, of course. So here, correspondences at time t are all correspondences for each observation I mean, we have like this for each of the observations, right? So this is actually a vector, and the dimensionality of this depends on the number of observations. And what is the value of each of these correspondences? It's an integer, right? And the integer, it's just the index of your landmark, right? So that's what I'm always writing, like this yi observation corresponds to the j landmark, right? So Okay, I'm just going to create like a little. Okay, at the end it's this. It's going to be just an integer. You will see this in problem set 2. This integer is given. And you just need to decide, okay, so from all my landmarks, which is this observation associated with. Here, because I don't know the number of observations, I'm just writing this vector. But you know here that can be all of them. It might be 0 if you don't have observations. It can be a million if you have a lot. Okay, well, maybe you don't have a million, hopefully. So we were talking about this distribution. This is how we are going to calculate the maximum likelihood after this first assumption that, okay, previous correspondences are conditionally independent of this, at least for the estimation of the current date for the current vector of associations. Then we are going to manipulate this distribution a little, right? And well, basically doing base, and here I'm writing proportional because there's going to be normalization factors. We can write it this way, right? So this likelihood function, yes, we can calculate it, right? So it's always the same problem. This distribution is extremely hard. What is this? Yes, this is an integer. How are we going to define this? But actually, this likelihood function, it's much easier to calculate, right? Because this, we just need to try, like different j's, given j's. Here we have this state. This is not going to change. And then we are just going to build an observation model, well, same as we did before. Okay, so, well, this will be like our posterior. This will be like a likelihood function that we are going to be using. Right, and it's going to be very related to our observation model. Okay, I mean, I could write here like more terms, but you just do base, and then you will see this thing. Okay, so now we are convinced that if we are looking for a maximum likelihood estimation, this is the distribution that we should be maximizing. Right? So in this case, this optimum, are we good on time? Yeah. This optimum of correspondences is going to be calculated in the following way. Right? So we want to calculate the maximum of this likelihood function. Right? And remember that for the maximum, variables that are not being optimized are not relevant. So that's why we are just saying, yes, this is proportional, and this is all we care. Because all the terms that are appearing here do not depend on C. Yeah. Okay, so yes, that's right. But this will be our prior on C. And for this, you can assume that this is just a number, or it can be incredibly complicated to calculate. Right? So this is the difference between map and just maximum likelihood. No, no. So this is a difference. If you want to take into account the denominator, this estimator is called map. If you don't want to take into map maximum a posteriori, if you don't want to take into account what is the prior distribution of C, okay, so this will be with respect to Y, right? Yeah. If you don't want to take this, then this estimator is called maximum likelihood. Right? Because as you see, we only have here the likelihood. With this, you will have like a proper posterior. That's why the other method, which is not the same, don't confuse maximum a posteriori and maximum likelihood. Okay, but in this approach, I'm not gonna calculate map. This is just gonna be maximum likelihood. You can actually derive map if, well, but then you need to think, okay, so maybe this is a task to think. I cannot really think now on a, yep. Well, the prior, it's going to be a variable that doesn't depend on C, right? It's going to be wait. Okay, so you do the base on this, right? Okay, if you want, let me write it behind or here. Okay. So let's do this, right? Right, everybody agrees that this is Bayes' theorem. Yes, thumbs up. Maybe I did something wrong and I'm testing. I think I did something wrong, right? Like this? Here? This thing? It's good. I mean, you are asking me questions, I can also ask you. But wait, so what were you saying? That this should be reversed, or what is exactly the point? Okay, so what we are saying here is that for this, this prior distribution of our correspondences, this is not something that we want to calculate, or we cannot really calculate. We can assume that this is some prior number which might be uniform or whatever you want, right? It's simply not going to be calculated for the optimization. And when you do that, this estimator is maximum likelihood. If we have like access to this, but imagine what is this exactly? So you have your state variables. With this, you can have a distribution of these correspondences. This prior is not trivial to calculate. So if we don't assume this, what I'm doing here, when I'm writing that this is proportional, it's, okay, so this denominator, it's not depending on, we agree that we can remove this, right? And here, what I'm saying is that this distribution actually, it's not informative. Might be uniform, might be whatever, right? And we are just removing. So that's what I'm writing, that this is, well, some constant variable that we don't care, okay? It's not that it's independent, that there are no other dependencies on C. It's that the maximum likelihood considers this distribution to be not known, and the only thing that you can do is say, okay, so whatever prior you want, like uniform, and then you keep going. If we had information about this, then it might be more accurate to use map, of course, but I think we don't. So then it's going to be, well, yeah, I think this is equivalent to having like equidistribution on each of these. So what is the most expected one at the beginning when you don't have any observation? Any landmark can be good. Okay, it's a good point. Everybody agree on this discussion? Is there something else you want to add? No? Okay. So then we are all in the same page, right? We want to calculate the maximum of this distribution that actually, yes, we can derive, but the only problem here is that here this set is actually a set of observations, right? So, yeah, I'm going to write it, and then we'll do because we still have time. So let me write it like expanding each of the terms, because here, this set, as I said, it depends on many, many terms. So in this case, at time t, we have first observation. And then just by doing the product rule, right, we are going to have like all the other observations, right? And then we keep doing the product rule, and basically it's going to be 2. Oh, this is K, right? This is number of observations. Okay, so we basically keep doing the product rule. Everybody sees here, right, that set T is this right? That this variable here, this random variable, in fact, is a composition of many observations, right? No? Yes? I mean, so I think this was explained in, yeah, when we were explaining this incremental update, right? We reasoned, okay, what if you have more than one observation? So this is just another way of using these multiple observations. This is a random variable, multidimensional, and then each of them is just each of the observations. We come here, we do the product rule, right? For now, we are not assuming any kind of independence, so that's why we cannot really factorize them just as I mean, they are not independent. For now, we are doing this assumption. We'll see later that, yes, we will assume that they are independent. But for now, just doing the product rule with any assumption, this is the correct form, right? So if you're not sure about this, redo this exercise at home. Have a large variable and start doing the product rule, right? So here you have this, you keep doing until you get to the last observation, and here it's just conditioned by this. Okay, so it turns out that yes, we have this distribution is going to be the product of many factors, but well, after the break, I'm going to explain what we can do to calculate each of them. But at least we have a form. For this one, which we already discussed, this prior, for instance, I don't have any good observation model. I don't have any other prior model that will give like a good distribution for this. So, but on the other hand, this, although might be long number of products, here we will have a observation model for each of them. Okay, so let's do a short break, talk about groups. This? This is K, but let me write it better. Right, remember that K is number of observations. We have another question? No? No. Okay. But you were raising your, no, okay. Okay, so 5 minutes. We'll be back. Okay. Let's get back. We have a few comments, so you might have talked about groups with others. There was one student that came and said that there's a midterm from another class, right, happening the same deadline as this, right? So who has finished who has started doing particle filter and finished EKF localization? We have 1, 2. You have finished particle filter? Okay, you're still. And what about the others? Who has not started doing problem set 2? Okay. I think it's a good time to start doing problem set 2, maybe after class. Because you can ask your colleagues that they have spent some time and they still haven't finished like half of the only 2 persons, right? Still, since there's this little interference with, I think, Tuesday midterm, right? Let's move this deadline for Wednesday, right? So I'm going to update things on Canvas. And what? We have another deadline? So I'm talking about problem set 2. Instead of being Sunday, like in 3.5 days deadline, which I think only 2 persons have got to the half of the problem set, let's move this to, but this is new hard deadline. I'm not going to move it anymore, right? But next deadline for problem set 2 is set for Wednesday. Okay, we can change the date on the assignment, and well, basically, I think what I hope is that everyone gets like submitting full problem set, right? Just because you have an exam, and then you maybe say, okay, I'm just going to submit half of it. I want everyone to finish problem set 2, right? But on time. So if you want to deliver it later, then there's going to be penalty, or you can use your Comodine or whatever name it is. Okay, so getting back to the class, we were discussing maximum likelihood estimator, right, of our correspondences. Here we have this distribution of our observations, now conditioned by all these correspondences. You can try at home, like doing the derivation, but here we have a hint, right, just base filter, assuming that this is constant or whatever. And then we want to find out a little more about this. And then we were discussing, this is the first approach. When you apply here the product rule without any assumption, this is what it turns out. You have k new distributions for each observation. And here we have conditioning each of these observations like all the other observations, right? So we know for the last one, when there's no other observation, conditioning this. But for this distribution, well, it's not so clear, right? So we are going to do now a second assumption, and it's going to be the independence assumption, right? So that way we are going to say, look, if you have a sensor that is observing different landmarks, there's not really a dependence between them, right? And this is a little subtle because there's dependence on the correspondences, as I have described. So the same observation or different observations is not really reasonable that correspond to the same landmark. But after doing the Bayes theorem and just factorizing things with respect to observations conditioned by other observations, from the point of view of the sensor, it makes sense to assume that your observations are independent. So if you imagine like one corner on the left is not really affecting what is happening on the corner on the right. Okay, so assumption 2. Independence. Okay, so now I'm just rewriting this likelihood function of all our observations, and after doing this second assumption, well, or approximation if you want, then this all these factors that we have here that the correct is conditioning them by the other observations, whatever that means. This, after assuming assumption, transforms into a product of these k elements, right, where each of these observations is independent of the other observations, right? So then, if you remove all the other other observations that we're conditioning, then what we have here is that this only depends on the correspondences and then on the state factor, right? So this is a second assumption on the observations. And well, what we have now is that independence we have discussed that gives like, simplifies things a lot. And in this case is this. We will have like, this is just our observation model applied here and nothing else. We simply have like a product of them. Okay, so comments, questions? I mean, this assumption I think has been done like in many other problems, I mean, from other topics, not in this course, but usually a maximum likelihood always turns out to be like some independence assumption, because then this thing becomes easier. Okay, so then let me rewrite again what is the maximum likelihood that we want. now with this well, distribution that we have obtained like in a better way, each of these terms we know, right? This is just our observation function, and we are going to be multiplying all of them. Here I'm just writing this because the only correspondence that we care is the one associated with this observation, right? And then we have state variables. Okay. Okay, so now we are going to do some tricks. And this is where, yes, these assumptions will basically pay off the assumption. Well, these assumptions will see that they are useful. So I'm just going to write it again, this productory. And I'm writing like here these, well, columns, right? And then what happens is that each of these distributions here, they have nothing to do with each other, right? So once you have an observation here, and especially a correspondence, it doesn't appear anywhere else. We just have these ones, right? So for the I observation, it only appears in this distribution. But others, I mean, as this index changes, it's not going to be dependent on that. So then what we can do is we can interchange, because this product, it's actually equivalent to writing this, right? So I'm just going to move things a little, but it only happens because there's independence here. These terms here only appear once. If we had like a correspondence appearing in other terms, right, because observations, well, whatever we have defined, but if this was conditioning other terms, we cannot really do this. But since they are, what we can do is that this is actually the product of all these okay, so this is only because each observation set I has like one only or unique, well, no, single correspondence. Right? So then everybody agrees. You can calculate this product, then calculate the max with respect to all these correspondences. So basically you need to go correspondence by correspondence inside here. But this is equivalent to just calculate the max for each of them, and then whatever is the result, you multiply it, right? So it's the same thing. There's not going to be a change. This is the subtle, but it's very important. Okay, so we have comments, faces, thumbs up if you are like, agree with this. And now you have a question. No, that's not relevant. That doesn't matter the number of landmarks that you have. Here in this observation model, number of landmarks, it's not really changing anything. The only thing that is changing is for each observation to which landmark you are. And here note that you can be repeating landmarks still, right? This correspondence, I'm not doing any kind of, this is the assumption of independence, right? That's why these things are gonna now look very familiar with another algorithm that we have described. But yes, landmarks here are just gonna be indexes. It's not changing the thing. The fact is that each correspondence only appears one for each of the observation, right? And there's no other thing conditioning. Okay, so, well, now we have this, and just to test if things make sense. Okay, well, no, let's discuss a little more on this. So we have this product of each of the landmarks. Now, if you forget about this number, we don't care about what is this number, whatever it's calculated, right? We don't care about it. then this approach, this maximum likelihood approach, with the assumption of, well, incremental solving, that the previous correspondences didn't matter, and the independence assumption turns out to be just the maximum of this, right? And what is this? Well, this probability definitely corresponds to the distribution of the observations, right? So this can also be reformulated if you do no, not the derivative, the minus log of this quantity, right? This will correspond to the minimum that we were discussing before, right? So in this case, maximum likelihood and well, the nearest neighbor Mahalanobis distance give the same result, right? Well, if we have like the right covariances. But here, it's also a greedy approach. We are just going max of them. For each of these correspondences, we are just matching each of them, and then we are looking for max. Okay. Question? Yes, please. Observations that are dependent. But I think on the terms of observations, it's hard to formulate. We will see that actually the dependence are more in the sense that if you have a correspondence to a landmark, you shouldn't have the same, you shouldn't have a different observation corresponding to the same landmark. So it's this principle of, okay, you are just looking for best association, but this is greedy again. So you are looking for, that's why in this case, it's not a good idea. I mean, it's still reasonable to say that observations are independent. It's very hard to find dependencies in observations, but what the tricky thing here is all these terms that we gave up when we were doing base rule, that this distribution of C of t, actually, it's not, we might have a little more information. And one of these assumptions is, yes, okay, so maybe you need to have like joint compatibility. You need to have joint correspondences, right? If you have observed a landmark, you shouldn't be observing this again, right? So this kind of context is not here. It's missing. From the maximum likelihood, we get nearest neighbor Mahalanobis distance if covariances match. Okay, so I cannot give you now an example of this independence. It simply falls down, but the idea, I think, it's more on the independence of correspondences. And in this case, they are not independent. We just did this base trick, and I think the prior assumption of removing it, as one of your colleagues was saying, was actually very strong, right? So, okay. Now, just as a reminder, this is the observation model that we are going to be using. So for each observation, remember, this is going to be range and B ring, maybe. Right? So this is going to be a normal distribution, center at whatever mean we have calculated. Now here, this depends on this correspondence. And this is an interesting thing. Before we were using the covariance only of the landmark, but actually this is not right. So what we should be using is, we should do covariance transformation of the landmark of the state, right? So here this is the part that we are transforming, right? Because we need to take into account what is the distribution of our xt. And then we also need to take into account what is the noise on the observation. Right, and if you remember, this Q corresponds to the noise of Z. So it's similar, but the covariances are not the same. That's what I'm writing here, that they are not matching. What I was saying before is, oh, you have this covariance on your landmark, but that's actually not the whole story. Okay. So, one question, where are the covariance of the landmarks here. Am I forgetting about it? Consider that this is EKF slam. I'm just saying, oh, forget about covariances. I mean, let's vote. So who thinks that I'm considering covariances here? Covariances of landmarks and covariances of the state X. Who says that we are just taking into account the covariance of the state X? Well, if you remember, the augmented vector was a composition of the state of your dynamic system and then all landmarks, right? And what I'm asking is, where is the covariance of the landmarks here? Okay. That's for EKF slam. Oops. Remember that what we did is we calculated Jacobian that looks like this. A lot of zeros, some terms, and then the only Jacobians that were not zeros was this with respect to X, to our state, and then there was another one that was with respect to the landmark, right? So here what we have is a large matrix, a large covariance. Here what we have is this thing with only these two things, right? So if you multiply this, as a result, what you should be having is the dimension of this should be dimension of set, right? So, well, set, I'm just writing it here. And then you can guess that the only things that you are going to take is this covariance of state X, covariance of whatever landmark is, and then cross terms, right? Multiply with the Jacobian. So this is what this, in this case, yes, this is a projection, right? But we cannot talk projection because it's not always a projection. But in this case, yes, we are doing covariance projection. More generally, it's just transformation. We get like some parts of it, right? And in this case, the Jacobian is saying how this should look like. All the other terms that are zero are irrelevant to our problem. We don't care what is the uncertainty there, right? So everybody sees that here we have like term of covariance of landmark, covariance of, right? No, many thumbs up. Okay, we have someone listening, maybe to some other class. Okay, so this is a good exercise for you. Why I'm telling you this? Because on the exam, I'm going to ask you about this, right? I'm going to write an example where you need to say, okay, which parts of the covariance have changed, or exactly what parts are you considering here? You need to think a little, not like, okay, so the formula is this, fine, sure, but what is actually happening, which parts, which blocks of the matrix have been used, and for this, you need to think a little, you need to start like doing some trials, maybe you start with NumPy and put there a lot of zeros, some blocks, and see what happens, maybe you do this by hand, maybe you do whatever, but you should be seeing this clearly, right? That if you multiply this kind of vector with zeros, the result that we should be getting is this. Okay, so this is a problem in the exam. Don't tell anyone. Well, tell whoever wants. Okay. No, what I ask is if this covariance that I'm calculating here for this observation model takes into account the covariance of the landmark. So if I was asking this now, would you say yes? Or you will still be, or this is just after this little sketch? Oh, okay, thank you. So yeah, actually we are taking everything into account because this is what we want, right? You cannot forget about other covariances because you don't like it. Here on the Mahalanobis distance, we were saying like some covariance. I didn't say which one. You can check this now. But actually the right way is considering all covariances, project them with your Jacobians, and this is what you have, right? So, make sense? Okay, good, awesome. Let's move on. So we have this. Yes, another interesting part is what happens with new landmarks. Right, and for this you can go to prop, well, to this page that they explain this a little more, but basically we cannot use this model for new landmarks because, well, we don't have well, no, we do have. Yes, we have all the observations, but then since we have calculated this with the inverse model, then we basically have there, I think, a linear dependency, and this makes. Okay, I'm not sure about this. But you should check definitely this in probabilistic robotics. What is the reason? But oops. But for new landmarks, what we have is this. So we have this, and this equals a new landmark, right? And this probability, the algorithm on the book, what they suggest is that we initialize this with some initial probability, right? And that's it. You forget about any other thing. So yeah, this threshold, it's always hard to calculate, but there's a good discussion on the book about this. Okay, so yeah. So the reason is if we don't set this threshold to be set, then we will never initialize a new landmark according to the maximum likelihood, right? Because the maximum likelihood is just looking for whatever is max, even if it's max of a bunch of very unlikely things, right? Maximum likelihood is just going to give you what is the best among whatever you have, even if all of them are wrong, right? So in this sense, maximum likelihood, yes, can be like a little problematic. That's why you need this threshold. So imagine you have here like all these distributions for each of them. I mean, all these probabilities given whatever observation. So all of them are terrible, like this is almost 0. And this is with respect to the correspondences, right? So in this case, it's landmark 1, landmark 2. And what this thing is saying is, okay, so you have new. If you are not below this threshold, if those observations are that bad that you don't get among these, then you should be adding a new landmark. If, on the contrary, you still have like a good match, then this actually is not doing anything, right? But this is a safety check, just to ensure that, okay, from all these very bad potential associations, you are still choosing one that is relevant, right? So if you choose like, I don't know, maybe this is the best one. If you choose this, this is clearly not a good association. So that's why you always need to consider like new, the probability of these new observations to be like some threshold. Okay, well, I think this is a little more detailed for implementation. Oops. Details on maximum likelihood estimators and all these things. Okay, so let's move on now to a little more interesting topic. I think we are going to talk a little about joint data association. Okay, and in this case, we have already said that, well, maximum likelihood gives us like good results, but this assumption of correspondences not really checking about the context might be bad. So this is an attempt to solve this. Right? So with this joint approach, data associations are going to be like considering what other correspondences are saying. Right? For this, the tree representation is very convenient. And let me write now what this tree is, right? So imagine we have the observation number 1, right? And basically, these are the hypotheses for Z1, right? So Z1 equals landmark 1. Okay. Another one. This observation equals landmark 2. This is another hypothesis, right? So we have for each observation basically the hypothesis that it could be any landmark associated, right? And then there's this new landmark, right? Okay, so this is just for one observation. Now what happens is that if we treat things independently, it doesn't matter the second observation, right? Because you just calculate max here, and then you move on to the next one. This is what we have discussed with nearest neighbor, and what we have discussed with maximum likelihood, right? With independence of observations. You just look max for here. Now, if we do treat like all these hypotheses like jointly, then what we will have is that when we consider the second one, for instance, in this case, we need to consider this hypothesis, and then the second hypothesis of landmark being 1, right? So this is going to be 1. For each, and you see here that this is going to be like all the combinations of landmarks and observations. This is going to be growing exponentially, right? So then we do the same for landmark observation 1, landmark 1, but now landmark 2, the other second combination is, okay, so we still maintain this, and second observation is observing second landmark, right? And we do this for each of them. So if you see the graph structure that creates, it's kind of a tree, right? So here we'll have like, for each of these first initial hypotheses, we have like second hypothesis that we need to test all of them, right? And the same happens here. So you see that depending on the number of observations, these hypotheses can grow like a lot, right? So at the end, the number of hypotheses are going to be whatever is left on the last layer, right? So these leaves at this last layer are the number of hypotheses. And this is going to be large. So, but this is the price to pay, right? This is a joint approach. If we want to have a joint approach, we need to test these hypotheses. No. Why? At the end, you are going to have the same combinations, no matter which order you take. Here, but this is the same instant of time. All of them are in the same instant of time. This is at the same instant of time. What you are seeing is 2 observations or 3, right? So no, it doesn't matter the order. At the end, what you are going to have is like the combinations of pairs or tuples or whatever number of observations you have. Yes. You leave all of them, and then you expand the tree for each of them. Yeah. Okay, so we have this, right? So this expands to whatever number, and the same happens for this. So you see that this grows like a lot. Order here doesn't matter for explaining the tree, but we are going to see that actually we don't have to expand the tree like in depth for each of the hypotheses. There's going to be like a very clever algorithm that allows us to do this a little more efficiently. Still, we don't have guarantees, but this is some of the best things we can do. Okay, so for start explaining this algorithm, let's define what is the individual compatibility. Okay, and let me again show like an example of this. So we are going to have here a landmark, well, with whatever covariance you want. And then we are going to have like some observations. right? And then let me write like covariances for each of them. Maybe it's something like this, maybe it's something like this, maybe it's something like this. Okay, so this individual compatibility, what it's going to be is just a test of hypotheses, just to filter out like those that are clearly not useful for us, right? So in this case, I think it's a good example. Here what we have is like 3 observations, right? And then we want to test this individual compatibility for this landmark. So in this case, we are going to be using the chi-square test. There's well, tables on this, like on the internet or somewhere else. I think that in probabilistic robotics you don't have a table for that. But basically what this is doing also, there's a reading on Canvas that refers to this work. So it's a work of Neighbour and Tardos from 2003, I think. But well, this algorithm that I'm explaining here, this is just obtained from there. With this chi-square, what we are going to define is a confidence level. And then this confidence level, it's basically going to say, okay, so we are going to test each of these hypotheses. And given that, well, on the table, the confidence level that we want, that could, for instance, could be like 90% or 95% or 99%, right? It's basically going to give you a number that we need to satisfy. And then let me write this a little more formally. So in this case, we are going to calculate a distance. This is a Mahalanobis distance, right? We are measuring probabilities at the end. And with this, the test goes as follows. So this is testing landmark 1 with observation 1. Covariance, we have discussed what it is, right? So we need to take into account both, but I'm just writing here this. And then what we are doing is, this is a chi, this is not an x, right? We are going to measure against this well, number that the table is giving us, if this basically hypothesis is relevant or not. So in this case, here giving like some covariances. Well, we have like some overlapping, doesn't really matter. At the end, maybe this passes the test. The same happens for observation 2 and landmark 2, right? This is also below whatever threshold we want to give. And then we go to this example, right? And in this case, this doesn't pass the test. Why? Because it's very far away, right? So whatever number, I'm just making up this example. Numerically, I'm not sure what it is. But you see that there are some chances that these hypotheses are correct, right? I think this is the idea for you to take. Observation 1 might be like landmark 1, and observation 2 might be that an observation corresponding landmark 1. But in this case, landmark 3, it's not very likely, right? So it's just going to fail this test, right? So, okay. So if you do this, you see what is the advantage. When we are building this tree, we don't have really to take into account all hypotheses, right? Not all of them are equally good. Maybe some of them are good, maybe others are not relevant, not useful, completely opposite to reality. So this is a pre-filter of this, right? So with this, we can decrease the dimensionality of the tree. Yep. Yes, can you ask again, because I don't get the... I mean that you think about success approach here. Yes. Yes. So in our case, the criterion is simply the distance. Well, this is Mahalanobis distance, which corresponds to a probability, right? If you want to take it this way, well, you need to do the exponent, right? But Mahalanobis distance, we argue that actually corresponds to Gaussian, right? So there's a mapping from Gaussian, from the exponent to this square form. Well, not square. Well, I'm not sure now if I should be including this. Yeah, but basically, yes, the statistical test comes from here. We are not making up these numbers. These are just Mahalanobis distance corresponding to the probability of each of them being there. Now the problem is going to be on the dimensionality, right? Because this confidence can be fixed. We can always look for the same kind of confidence, but this number is going to change with respect to the dimensionality. And we'll see that for one problem, for one-dimensional problem, this is okay. But the idea here is to have a joint compatibility test, right? So for now, I'm just describing this for one single individual landmark, right? And then we will build the other necessary things for, well, more than that. But I think, yes, the test, I mean, I'm just referring you to this. I'm not going to explain like a chi-squared test. But I think, yeah, I mean, for the understanding of this derivation, this is what we are going to be doing, checking Mahalanobis distance. Okay, everything, comments here? Okay, yes, we have a question. These are examples. So given this confidence level that you are setting, and this is a decision from your part, what you can say is what is the probability of this hypothesis being correct, right? Why? Because then you can reject very easily like those that are clearly not under this confidence. Depends a little on you. Basically on the table, yes, you have like very high confidence levels, I think 95, that depends. Depends on how restrictive you want to be. You can try several. At the end, this is just a lookup on a table. Okay, so now with this, I'm going to define like, this is the individual test. Now the joint compatibility test, because this is the more interesting part, right? Not really filtering like each of them, which is solving a little, but not really solving our problem, but joint compatibility test. This is what we want. And as I said, there's this paper on Canvas, so you can take a look if you want. All the formulation that I'm using is from the authors. So if you want to check the paper, it's there in Canvas. Oh, 2001. Okay, so as I said, the intuition is context gives like some information. Right? And in this case, it's going to help us like verify some hypotheses and reject others, just based on the context. So context provides accurate solutions. Okay, so we have discussed that this set of hypotheses basically grows exponentially. There's always the brute force approach that you can use, by the way. So you just test this joint compatibility for each of them, and then you just take max. Right? So forget about this shift that we did. Max inside the product. You leave out max. And then what you do is this product of all of them, but then the hypotheses by themselves are checking like this. So no. With this, no, you will not get any better. Okay, so basically we need to find not just the independent distributions for each of the observations, but we need to find like some consistency between each of them. Okay, so for that, let me rewrite like this is going to be the set of hypotheses. Like for instance, this is one of our hypotheses. We are going to have a lot of them. Well, maybe instead of this, I'm going to use L because, but basically here we have like any hypothesis that you can imagine, right? We are just making already like this. In this case, we have 3 observations, so we have 3, all these 3 correspondences. Okay, so then the idea is that for each of these candidates, what we are going to do is a joint compatibility test based on the same chi-square function that we define. So there's going to be a value, right, calculated after each of these hypotheses. And then what we are going to do is define a confidence interval and then check, right? So is this like good in our, is this hypothesis something good that is belong these intervals of confidence or not? Okay, so now we'll see. We'll see how to do this. Check for vector of correspondences. As I said, the difference here is going to be on the dimensionality. So now what we need to do is define this function, right? We are going to define this function that is considering all of them at the same time, right? And the key thing here is that, as I said, on the independence assumption, it was a product of all these distributions. Here, what we need to take into account is proper cross terms, right? In the hypothesis that we will be generating. Okay, so for the individual compatibility, I'm just putting like a little more formulas, but it's the same idea as before. So this is just for one landmark. I'm going to define a function, and this is going to be useful because later for the hypothesis composed of several observations, we want to stack these functions, right? So at the end, it's going to depend on I and J. I, remember, that is for the observation, and J is landmark, right? But, this is the nomenclature of the authors. Here we have like augmented state vector, for instance, for us, and then an observation. And then this is going to be like sort of a residual, right, where we are just measuring this distance. The observation that we have and the observation that we should be seeing. So this is the same as we did before. If this observation was perfect, this should be 0. Right? The idea is that the lowest this number is, it's going to be better. The hypothesis is going to be closer to be more likely. If it's large, this number, this residual means that there's a mismatch. Maybe the observation is not right. Maybe there's some noise, or maybe it's totally wrong observation. Okay, so this was from lecture 5, right? This observation model. It's again based on landmarks. And then if we want to build this is the individual compatibility. If we want to build the joint compatibility, I'm going to just do a similar thing than what we did for the augmented vector. I'm just going to write here like a function for the whole hypothesis, right? And this only depends on the state, augmented state, and then all the observations. And here what we write is for the individual compatibility, it was just a number, this residual, right? Saying, okay, how much this matches. Ideally, if everything is perfect, this equals this, right? So our function will be 0, and if we don't have noise, then there's not really a matter on, we shouldn't care too much on doing the correspondences. Everything is known. But since we don't, we need to do this. So I can write like all the, for instance, this is for observation 1. So this is the correspondence that we find for observation 1, right? landmark. Okay, so this is basically a vector of all the observations, right? So here we have for observation 2 corresponds whatever landmark we decide, right? And then we keep doing this until we get to the Lth observation, right? And in this case is the observation L. I'm just following here notation from the paper. That's why before here I was using I, but well, you will see in a moment why the difference is important. Right, and then we have now all these stack functions. All of them are trying, remember, are trying to match the observation with this model that we provided, right? So the closest they are, that means that the better, the closest they are means that this is more likely to be like the observation of that given landmark. If it's really far away, then it's not a good correspondence. So this is true, but we can also write this in incremental or, yes, in incremental form. And for this, let me write it this way. So here, I'm going to write this, the hypothesis of L minus 1, and then here I'm just writing the last number. Okay, so what I'm doing is grouping all these previous vectors, all these previous hypotheses, I'm grouping all of them together into this, right? And if I have defined like this function with respect to the hypothesis as these stack vectors of all the observations and correspondences, we can also write this in incremental form, right? So here we have all this stack and just the new one, right? So it's this hypothesis of L minus 1 and then this new observation matching whatever landmark we want. Okay? So far we are just grouping things, defining things. It's like, yes, we have a large residual. Now, instead of being for a single landmark, it's for many, many of them. Okay, so also, yeah. Yes. Yes, but yes, so if it helps for the understanding, let's not use L here. Let's use like we have like any hypothesis. This is the full stack of all the hypotheses. I'm just writing L because this is the intermediate variable that allows us to build these hypotheses incrementally. So we take all the previous ones plus a new one. Imagine when you are building a tree, you just care about the current branch, and then you just expand last one. So this is a similar thing, right? You are taking into account all the previous hypotheses that were done, and you are just adding a new one. Right? So it's kind of growing the hypothesis. So this is like, in general, like hypothesis consisting of all observations and matchings, and L, as I'm writing here, it's this growing or nested set of hypotheses, right? Observation, exactly. Yes, this is for observation 2, so you need to do this for each observation. If we go to the tree, it's actually a good comment. I'm going to spend a little more time. So if you go here to the tree, as this is built, well, right? So this will correspond, oh no, this doesn't correspond to anything. Well, this is the first observation, this corresponds to the second observation, and this corresponds to the third observation, right? So basically this is the layer on the tree as you are doing. So we are doing the same thing here. I'm just defining all the previous correspondences, right? And then I'm just adding a new tree, and then this could grow as much as you want, right? So this is a way just to do this incrementally. We'll see the advantages of this when we do the hypothesis testing. Yeah. No, this is not all observations. This is just some number of observations that we grow. So, yes. So then this L denotes kind of the level, the depth that you are considering here in your tree of the observations. Yeah, that's another way of looking at it. Okay, so then we'll see what's the advantage of doing this. But so far we are just grouping things and redefining, and okay, things look, there's not really an advantage for this. But we'll see what is the advantage in a moment. Let me just rewrite things a little, more clear. Right, so this is the hypothesis that I'm writing here. This will be like the, well, hold on. Yeah, so this is like any hypothesis, right? Here we have correspondence 1, correspondence 2, correspondence k. Right? And then here, for instance, we'll have this H to be 1, right? And this corresponds to this part here. Now, we can do the same for the second one, or we can do the same for whatever other number, right? So in this case, this will be H2. Right, it's considering these two, right? And then if we keep doing this, so this will be like H, I don't know, L, whatever. It's not including all of them. It's just including like some of them. But this is a way of growing the, let's say, dimensionality of your hypothesis. You are adding them on an incremental way. Okay, and what is the advantage of this? So I'm just going to show now. So, well, we have defined this, so now we have this incremental part that we know that equals previous one and set, and then we have here okay, so what the authors were proposing is let's approximate this by a Taylor expansion. So we have done this many times before, but this is kind of a strange thing. We don't know exactly what this residual is. It's just matching, like, it's kind of a vector of innovation vectors. Of innovation, yeah. So here it's this, right? So it's kind of what we have here, all of them stacked for each of the observations. So we have them, and then what the authors were proposing is let's take the first order expansion. Why is this? Well, because you'll see that with this, we can actually create like, this is just the Jacobian with respect to the observations, right? With this, what we can do is these Jacobians are going to be large, but they will allow us to take like these cross terms as we were saying, right? So the compatibility test comes actually from the relations that appears in these Jacobians. So how we move from here to here? This is it. No, I'm just doing Taylor. So that's what I'm approximating. You just take this function. Remember, you are stacking here all of the observations. You do Taylor, evaluate at the mean. Jacobians with respect to the state variable. Jacobians with respect to the observation. That's it, right? We don't need more. The only strange thing is that here, what is this, right? Is this an observation? Well, we said that this is the vector of innovation vectors, but, well, after doing this, then we can have the covariance of this hypothesis, right? I'm going to write here like this index saying that this is a given hypothesis. The authors actually use for covariance the letter C. right? And then it's going to be this. So we have this Jacobian, well, covariance. Okay. Yes. This. See. This is how they use letter for covariance. Although we, in our course, we were using this capital, they were using letter C. So I'm just following the notation on the paper. No. Alternative notation. Okay. Let me write it this way. Or. Okay. Yeah, so don't mix. So that what we have is after, okay, so you can take later a look on how to obtain like these covariances. So this is known for the state. This is for the observations. But then later what we can do is calculate like this value. At the end, this is a value. But this one is taking all correspondences into account, right? So it's taking not just like independently each of them, but it's actually taking all of them together, right? So it's going to be this, right? And this is a little complicated then to calculate, right? But, well, we didn't say that this was easy because we need to do the inverse of the matrix that is going to grow. It's going to have like dimensions, and then basically the test is going to be this, right? Is this going to be below the chi-square test? Okay, so far we haven't said anything that will help from the point of view of the algorithm, right? All I'm saying is that, yes, you have a lot of hypotheses, you group them incrementally, and then what you are doing is calculation of this, right, which requires an inversion, and then, yes, you have a, but still, we haven't solved the problem on how many of these hypotheses do we need to test, right? And this is where the, I think, main contribution of the, of this approach comes in. So this is the joint compatibility test, but then there's a second part, which is called branch and bound. And the idea is very simple. So the chi-squared of the parent it's always smaller than the chi-square of the child, right? I mean, on the worst case, it's the same if you had perfect information. So that means that, yes. This is the covariance of this new vector that I have defined, that for calculating this, you can do it this way. So depends on the covariance of your, no, not just of observations. Everything here is included. And this is the covariance of observations, which I'm not sure what it is exactly, but I will leave that this depends on the, so maybe this is a block diagonal of Qs. I need to test this on the paper, but definitely this is the covariance of your augmented state. This is a large matrix including positions, landmarks, and whatever you want. You have a Jacobian that you don't know what it is, but it's considering each of the hypotheses, and then you project this covariance into these new covariance that we are defining here, right? So this is a new thing, just to calculate this distance for the chi-square test, right? So that way, we are considering all the hypotheses at the same time, like jointly. Yes, 1, 2, and 3. Yes. See, this is the result. This is what we are looking for, right? Because later it's used here. Well, this is the covariance after assuming that your vector of f actually it's a transformation of observations and, well, of the observation function and some observations, right? So when you have a stack vector of this, and since this vector is obtained from the state variables and the observations, what you are doing here is just transforming. So this is a linear, well, non-linear transformation of a random variable, and we have described what to do. So we do first order linear approximation. Here in this case, there's no necessity of doing any linear because this is already linear, but for H we need, right? So this is covariance of the vector of F, yes. Yes, yes. This is, well, S, you should check it on the paper. But this depends on the observations. So I believe that they will be using Q. But I cannot check now for sure. Okay, so what is the cool idea? After doing all this, after stacking all these vectors, I'm almost finished. So the idea is that this chi-square is not going to decrease magically. If you have a bad hypothesis, it's going to be bad, even if you add more terms. Yes. So what is this thing saying? That you add a new hypothesis. You add a new observation corresponding to some landmark. You add this to the parent, which is already taking into account some correspondences. But it doesn't matter what you do here. If the parent is already bad, okay, no. Wait, I don't want to say it this way. If the hypothesis on the of the parent hypothesis is already unlikely, the child is not going to be more likely because you are already considering like all these terms that are not likely. So it's not going to change. This chi-square grows monotonically. So in the best case, even if you had perfect new hypothesis for the child, it's going to be as good or as bad as the parent. So this is good because with this you can branch a lot of, you can basically bound a lot of branches, right? And what it means is if parent is already like not passing the test, you just come here and you don't keep propagating things, right? So in terms of graph search, what we are doing here is, this is not a, so yeah, I think this is well, it's kind of funny. Okay, let's not mix with graph search. But basically, once you start like doing search over this tree, and you hit like a point where the parent doesn't pass the chi-square test, you don't keep propagating, you don't keep expanding the tree below, right? You just go deep on all those hypotheses that are already good and promising. And you can detect them early if they are like above in the tree. In the worst case, this has like, the complexity of this is exponential, right? You need to go over all the hypotheses if grown correspondences are at the very end. But in the best case, this can be just as bad as maximum likelihood, right? You wouldn't be doing like more than that. Yep. No. This is a property by construction, so you can do it. You just write the vector, you add a little number, and then you compare with respect to just not the augmented vector. It's always going to be, because this is covariances are positive definite, right? So you always have like something that is summing in the worst case, right? So it's always going to increase, right? That's the point. That's the only important idea after this derivation, that you can branch a lot of, you can cut a lot of branches, and this saves a lot of time. So for hypothesis testing, this kind of approach is useful. Yes. Wait, so you're asking if there's a unique solution. I think what you're asking is if you will find the same solution persistently if you permute the order of observations. Right? If there's a solution, I think it's well defined. Right? Definitely we don't have here like local minima or these other kind of problems. This should be very clear. But with different permutations, yes, I think you should be getting the same result. What it's not the same is the number of evaluations that you have to do, right? Because maybe you need to go like deep on the tree until you hit like, oh, okay, so after this level, okay, this was like reject on the test, but all these previous levels were like passing the confidence test on the chi-square, right? So the order, it's not affecting the solution, it's affecting the performance or the efficiency of the algorithm. Okay, so there's some comments here, grading here, but I'm just gonna read them. Basically, we are capturing all these cross correlations, right, of one correspondence, taking into account like the other, like one landmark and the other observation taking into account the same landmark. This is gonna be unlikely, right, because we are building things like jointly on the same, I mean, the vector of hypothesis is just growing. We don't have assumed any independence here, right? And remember the trick on the maximum likelihood. So after doing base and then saying observations are independent, some magic happened, but actually the trick here is that correspondences are dependent, and we are capturing this dependency here. So we are not doing this trick from the maximum likelihood. Probably this is more accurate, right, for complex examples. And it's probabilistically more complete because we are giving like a proper, well, calculation of all these hypotheses like jointly. On the other hand, it's very slow, right? So here you have the inversion of a large matrix. This inversion keeps growing. On the worst case, you might be evaluating all the tree. But if you want to have like, well, good data association correspondences, maybe you are willing to pay this price, right? So maybe you are more interested in having like correct information rather than having things like calculated very fast. So this is an algorithm for you to know. It's now on your tools. You can always start just with maximum likelihood, do covariance transformation, and that's a starting point. And then maybe if you need like more certainty, JCBB can be a solution for you. Okay, so there's a lot of variance on this algorithm. Well, I believe that now with more neural nets, there's like cooler things that you can do, but still the idea of context is important, right? So landmarks are actually not that trivial. It's clear when you have the math, when you have known correspondences, but how to calculate these correspondences is also part of the problem, right? And sometimes it's a little not treated properly, but still this can affect like highly what is the quality of the algorithm that you are calculating. Okay, so for next lecture, we are gonna explain GraphSlam. Here, well, we will forget a little about filtering. We are going to be calculating full trajectories. It's a kind of different paradigm. I'm going to explain, I mean, there's going to be a couple of lectures on this. It's very exciting. Actually, this is like closer to the state of the art. I don't think it's possible to get like directly, well, you can start explaining GraphSlam without explaining filtering, but with this you get a lot of insights of what are the peculiarities on localization, state estimation, and mapping. So next lecture we are going to move to this. There's readings at the folder, right? So you can read Dellard's paper if you want to have an introduction, or there's like class notes available in Canvas. Okay, so see you next Tuesday. Goodbye.